presented by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. This show is funded by supporters on Patreon and Subscribestar. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Hello everybody! I hope everyone's having a beautiful day. I'm just going to check on a few things. Just going to make sure we got our levels right. I'm just going to make sure. Just give me one moment. I'm just going to see. Okay, good. I can at least see that. Okay, good. Other than that, let me just, yeah, that should be okay. Okay. Sorry about the delay. So, hello everybody! I hope everyone's having a beautiful day so far. So today we're going to be talking about searching, in particular the fundamentals around searching. So I would like to talk about kind of what goes into solving a basic search problem. We're going to talk about a couple algorithms here today. And in addition to this, I'm going to talk about some lower bounds. You might ask, Dan, what does that mean? We're going to be talking about all of these things here together. So I guess before anything, I should get into what exactly do I mean by searching? What does that mean? What is that as a problem? So I'm going to keep things rather basic for us talking about this. So I'm going to start off by defining the search problem. So just to keep this rather straightforward for us, I'm just going to give you kind of a definition here. And keep in mind, if you're in the chat or if you're watching this feature, feel free to ask any questions, or if you have any comments or anything like that, let me know. Little things like this are always what make these things a little bit more unique than otherwise. So please, I encourage you to participate. It's a good time. So I think it'd be a good idea before I get really into everything, I kind of lay out some of the key things we're going to need so when we actually start talking about this stuff, we got it all. So the search problem, we're going to presume I'm given some collection of elements. Now for simplicity, now you might ask, Dan, what does that mean? So say, for example, you may consider like a list of numbers. Or you may have, for example, an array that has a bunch of numbers in it. Or perhaps you have an array that contains a bunch of words in it. These are a variety of different things that are different kind of collections. We're going to focus on keeping this rather simple as possible. Now, all I'm going to be focusing in on is presuming that my collection looks something like this, where I have what we call an array. So each one of the positions has an index, which like these numbers here. So this is the start of the array. This is the first position, position 0, position 1, position 2, position 3, position 4. So for each one of these positions, it may have contents at that spot. So in our case, for simplicity in our discussion, most of the time you can just think of these just as numbers at these spots. So for example, if I access at a given spot, so if I call this array, say I call it A, for example, we'll call it A. Suppose I have array A, that's the name of this collection of elements. If I want to index into a given spot, I would say A sub, I'll use these square brackets, the index in here. This is just some notation we're going to use to make this easier for us to understand. Is I can put in an index that gives me what's inside this box. So for example, if I give A sub 0, if I try to access this, I would go to this location for my array, and what would be there? The number 3, right? So in this example, A sub 0 is equal to 3. So this is just the name of the array. So this is a name that we've given it, so you can think of it as just a variable name. This is its index, and it will have some value stored there. Furthermore, you could also reassign a value in an array, but for us it's not going to be too terribly important here. So the point is that we're going to have these collections, and keep in mind, a lot of our discussion will be fairly easy to generalize to other kinds of collections than just arrays. So this is just to keep things rather straightforward. I must warn you, one other assumption I'm going to be making in this discussion is that I can access any one of these positions in constant time. That means if I give you an index and I want to know what's at a content of any one of these spots, it should be able to tell me, hey, look, it's at this spot. So give me the thing that's right there. I should be able to instantaneously grab it, but this time should be independent of, say, the import or the length of this array. So that's what we're going to be talking about here. So what's the search problem? Well, with that being said, let's kind of move into this. So anyways, today we're going to be talking about the search problem. We're going to be talking about some algorithms, and we're going to be focusing in on lower bounds. I thought before I get into anything too delicate, let's start talking about what the search problem is. So this is how we're going to define it. So we will be thinking about this for our discussion over an array, which I've discussed a little bit here, but as a reminder, it is just, imagine you have a collection of elements, each with an index, and I can access any one of these indices. So if I give you some number for an index, I should be able to grab what's inside as the contents of this spot in the array. So for example, if I want a sub 1, I should be able to get this number 5. So that's at position 1. It starts at 0, goes 0, 1, 2, 3. These are offsets from the origin address if you think about this from a computer standpoint. But remember, it is just a construct of the definition of just a linear collection of elements like this. But I won't go into too much about that. So presume I am given an array. Let's call it L. Given an array, well, and a value. Now, I'm not going to say what kind of value. It's just a value. It could be a number, it could be a word, it could be all sorts of different things. And a value x is x in L. So if I look at one of these boxes here, if I give you, say, some number for our example here, can you tell me if that number is somewhere in one of these boxes? Yes or no? True or false? If it's true, that means that it's in our array L. If it's false, it means it's not in any one of these boxes. Now, there's several different ways you can cast the search problem. For example, you can have it where you just simply ask where it is. So you can ask, if I give you this value x and L, tell me the location where it is if it exists. Otherwise, spit out -1, because that's on an index here. Notice that -1 doesn't exist right here. So it's a safe value for me to use, given no matter how big this array gets. That's one way I could go about this, to define the search problem. But like I said, you can define this also on all sorts of other collections. You can even think of it as just a set, where the set is just an array that's being representing that given set, which is easy enough for us for our discussion. So if I use the word array here, you can easily switch this out for the word set for the definition of the search problem. Hopefully that's clear, everybody. But the big thing is that we're just going to make this presumption because it's easier enough for us to talk about at this level. So I thought, let's talk a little bit about how we could go about solving the search problem with like no assumptions about what is in these boxes. So I think it'd be a good place for us to start to talk about how could we solve the search problem if we're given an array L and a value x. How can I tell you that x is in L or not, as in it's in one of these boxes? Well, let's think of the most basic thing you might try doing. Now remember, when we develop an algorithm, which is an unambiguous, that means no matter how you read it to somebody, they're not going to misunderstand you. There's no two different interpretations of this that are going to lead you to two different outcomes or anything like that. It's going to be unambiguous. It's a step-by-step process where I give you input, in this case L and X, and it may even give me another parameter. Say, for example, you may want to know the array's length. Like, say if here I have 5 boxes, I may have that as well as one of the inputs too. So I have these two. I want to know so I give you inputs, it gives me output, and we want to know when the algorithm is correct. That means that the output is going to be what exactly should match for that given problem. Every one of the instances of this problem is an array with some value x. And keep in mind, there could be many, many, many different values for x, and there could be many, many values for L. So that means that it doesn't have to look just like this one. The array could, for example, have not just 5, it could have, say, 10,000 elements, each one with a value inside of one of its boxes. And the question is, okay, so how exactly can you search in such a construct, like this collection here? Well, you have to keep in mind, we can't just simply just come up with something on the fly and be like, yeah, look, you just always pick box number 3 here. Just if you pick that one, you always will find it. See, that's not going to cut it probably to solve this problem, because if you think about it, suppose that value x was, say, in this box instead. You couldn't just simply just pick box 3 every single time, right? We might need to do something more systematic, right? We can't just simply just guess one of these and say, that's good enough, right? That's always going to give me the correct answer. So I have an interesting proposal. It's one of the most first things you might think of trying to do is as follows. Well, suppose I was looking for the number 7. Suppose that x is 7. So let me just draw a picture to help us kind of walk through this process. So I'm going to have 5 boxes. So I'm going to show you what this instance will look like. So I have my array. I'm going to call this one L because that's the name I gave it here. And it's going to have positions. So 0, 1, 2, 3, 4. Just like I have here. 0, 1, 2, 3, 4. And now there's contents in each one of these spots. Now, one thing I really want you to pay close attention to is that I need to have this developed in a way, because keep in mind, I'm making no presumptions what's in these boxes, right? It may as well be that I don't know what's in these boxes, in these spots in the given array. So I won't know until I check. So it wouldn't matter if I knew what position 2 had, or like box number 3 always was some value. If I could tell you that up front, it wouldn't make any difference because I might give you another instance where x is somewhere else. So I want you to kind of keep this in the back of your mind. This will be helpful for us to start thinking about how efficiently we could solve the search problem. So let's start off by just doing something I would consider pretty logical. So if I don't know where it is, and I have these indices starting here, perhaps it might be a wise idea to start right here, stay at position 0, check here, see if it matches x, and if it doesn't match x, then we go to the next box. And we try this again, and then try this again, then try this again. Well, let's see. Now, keep in mind, in our instance, we also have it where the value x is 7. And in the event that we need to know an n, in this case, that's the length of this array, we have 5. So let's kind of go through this. So at position 0, let's take a look. Okay, so we have a 3. So 3 is not 7, right? So we know that does not equal 7. So far we've considered this one. Next, let's look at box 1 again. Let's remind ourselves what's in here. It's 5. That's not 7. Okay, so let's check box number 2. It has a 2 in it. Isn't that lovely? So it has a 2 in there. And now let's check box box 3. See, if you went with box 3, you'd get a 6. So in this case, a basic approach of picking at index 3 every time won't cut it, okay? So box 3 had a 6 in it. And then, of course, let's check the last one. Let's see. Look, it's a 7. Look, it's the 7. We found it. So in this case, we can answer yes, true, that it is that L contains 7. So it was just sitting in position 4. So in this case, the solution is true. And of course, the position it was at was not 7. That's the value that was at that position. It said it's 4. This tells me where it is. So in the event I'm returning back position, I'll tell you 4. If I just want to know if it's there or not, I could just tell you true. Either one of these will tell me the answer to this instance. Naturally, you can easily translate an answer like this into one that's like this. Because if I give you a number that is some non-negative integer, this will cut it. Because that will tell me that, yeah, it's there. So hopefully that is clear, everybody. So what I've just described to you, this process of us walking through each index for sweeping it from left to right, is something we would call a sequential search. I go through each element in my collection. And in particular, notice that this collection is linear. So we actually call this algorithm, the one I just described to you in our example, we call this linear search. So if you have linear search, you can, so here's the big catch, is I would like to know if this always works. Now, it's very easy for me to be like, oh yeah, well, we check all the boxes, so we're all done, right? So we know that this is obvious. It's obvious that this is correct. Now, that's what somebody that isn't thinking about this rigorously might tell you. They might tell you something along the lines of, oh, well, we check all the boxes, so most certainly if there's nothing else, if I've compared all of them, then most certainly there's nothing here left, right? Well, that's one thing you can argue. Most certainly that is a true statement, is that if X exists in L, then most certainly checking all of them will cut it. But we want to be a bit more rigorous with this. We don't want to just say that. We want to say, why is it correct? So there's another way you can approach that same rationale to show that linear search is in fact correct. So I thought what I will do is I'm going to show using what we call an invariant. I'm going to show you how you can prove that this algorithm is actually correct, given this setup. So I'll first, after I identify this idea of an invariant, I will show you what linear search would look like if I wrote it out in pseudocode. Pseudocode, for those that are not initiated to this idea, is that very often people like to describe algorithms in a way that it's very easy to interpret and there's no ambiguity. So one standard way of doing this is trying to adapt the ideas that we have from computer programming. So for example, we would communicate in a programming-like syntax that isn't specifically tethered to any one language, though sometimes people will try to tether it a little bit to one language to help you understand some of the ideas, say if you're familiar with one language. But the whole point is that it's not really related to that. We want to describe the algorithm in a machine-independent way so that you understand the algorithm. It doesn't matter if we did it with boxes like this. It doesn't matter if it's on a computer with 16 cores in it. It doesn't matter. It doesn't matter if it's on a supercomputer. You should know, like, if we try implementing or describing linear search, its description does not change. So ultimately, what you do doesn't change, but the way I could describe it may change machine to machine, but the way I want to describe it to you, it shouldn't matter. That's the point. Because it's an algorithm. It's a formal concept. So anyways, I want to talk about this idea of an invariant. So what I would like to do, so this is going to be something I really want you to pay attention to when I write out linear search. So an invariant, at least for our discussion, is to come up with so this is a property or relationship that is maintained during the execution of the algorithm. So there's specific kinds of invariants. The one that we're going to be using is what's called a loop invariant. So what this will mean is that every time I perform one major step or main iteration of what we call a loop, it maintains a special property, this invariant. And if we can ensure that this invariant always holds during each what we call iteration of that loop, if it happens each iteration, so before and after the iteration it maintains this property, then most certainly you'll maintain this property at the end. And naturally you just look at what happens at the end in relation to what the invariant tells you. So you're going to see this in a moment, okay? So let me describe linear search for you. So the big thing here I really want you to pay attention to is just how I describe this to you. So I'm just going to keep this rather simple for us. So we're going to talk about this algorithm. Usually when I describe an algorithm to you, usually it's a good idea, and this is just generally a good idea, is you describe what the algorithm is. You need to tell me what the input is and the output is. That's the framework that we use for problem solving in this setting. It's pretty common for computational problems. So suppose I give you L, N, and X. Just for sake of simplicity, reminder, N is the length of the array. Now you might ask, Dan, why would that matter? In some programming languages, you could just get the size or the length of an array, how many boxes we have, using library calls. Some programming languages, it's handy to actually have the number. So some languages, getting that is not as straightforward. So input, so I'm going to give you the array L of size N, and we're going to be given a value X. So I have L and I have X. So as output, I'm going to tell you it's going to be outputting true. Is true if X is in L, false otherwise. So it's either going to give you a true or false. If X is in one of the boxes, like we had over here, then it returns true. The algorithm will return true. Otherwise, it returns false, meaning that it's not in any one of the boxes, any one of the positions of the array. So the first thing I'm going to do is I'm going to make a variable. This is going to be some sort of Boolean flag. Now, you might ask, Dan, what does that mean? I'm going to make this variable. I'm going to work under the presumption I have not found it yet, or that it just simply doesn't exist, because I simply don't know it does or not. It should remind you of something I said just a moment ago. So I'm going to presume I have a variable. I'm going to call this found. It's going to be set to false. This is because I want to just presume it's not there yet. If I encounter it, what I'm going to do is I'm going to flip this to being true. So if I can change this to true, that means that I've encountered X somewhere. And then when I'm done, I'm going to return if I found it or not. See, it's pretty logical, right? So now we're going to go through each one of the boxes, one after the other. We're going to start at index 0. So that's the first position, our leftmost box we had over there. So I'm going to have a counter variable. I'm just going to start it off at 0. So these are just assignments, by the way, just to be clear. So I'm assigning I to be the value 0. And it's going to check all of the positions. Notice that the last position is always one less than what n is. So now for each one of these, what did I do over there? What did I do over here? What did I do? I checked if in the box there was X, right? So that's what I'm going to do, just like we just described. So L sub I is equal to X. So I check if that is the case. If this is true, then I want to flip my found variable so that instead of being false, it's going to be true. So if I find it, then I'm going to update found to be true. So it's not false anymore. Now keep in mind, suppose that X occurs multiple spots in this array. It wouldn't make any difference. It will stay true. It never sets it back to false. Just please take note of that. There's nowhere in this loop now where it sets it to false again. So just keep that in mind. So the minute it finds one instance of X, keep in mind X may appear multiple times. Doesn't make any difference. Then after, we just return what found is. So whatever found is at the end of this process, that is going to be, what we're going to claim is that it's going to give us this as output, and it's going to match up in these cases. So it's going to be true if X is an L, meaning it's going to solve our search problem we had over here, our basic search problem. So you might ask, Dan, what exactly is the invariant here? Now, there's a lot of ways you can think about this linear search. There's a lot of different things you can think about. But I want you to think about this. So let's think. Let me draw a fun picture over here. And you're going to see very quickly that it didn't really matter a whole lot that I knew or didn't know exactly what was at a given spot until I examined it. So check this out. Let's think carefully about why it is the case that linear search, in fact, will correctly output true if X is an L. So just a reminder, remember to notice found is set to false at the beginning. So if X is not found yet, found is not updated, right? It still stays false. That seems pretty straightforward, right? At least I hope that is. So just notice this. This is an important detail. So now, take a look at this. So suppose you have this array. And suppose that we had our lucky 7 was sitting right here. Suppose that that's where X is. Okay, in the first iteration of that, if we walk through carefully what we did earlier, in the first iteration of this loop, it starts off at I at 0. So what it will do is it examines this position and says, uh-oh, in that position, there is nothing, right? So then it proceeds to the next spot and checks if L sub I is equal to X. Well, notice the next spot doesn't have X in it. So, oops. Go to the next one. Okay, there's nothing there. I'm going to keep going. Notice each iteration, there's something interesting going on here. Does anybody see it? Do you notice that every time I don't find one, notice that, or even heck, if I do, notice that every time I do one iteration of this loop, I've examined all the ones to the left of the position I'm looking at. So for example, when I check this position, all of these ones are already examined. Does everybody see that? So it's the same idea we talked about a little earlier, just that, but we've got to be a little more rigorous about this. We can't just simply just assert that, oh yeah, the algorithm for sure will check all of them. We need some way of connecting this up to that the algorithm actually does. So that's kind of our high-level description. We need an actual explanation. Like that's a high-level explanation. We want a formal one. So naturally you would check this one, that doesn't match. But notice that it gets to the last one, and then you say, hey, look, it's right there. But notice that I have had to have checked all of these to have encountered that true value of X, right? Where all of these other ones, I didn't find it. So here's something we can think about. So let's think about how many iterations are going to be happening here. So notice that it starts off at 0 and it goes up to n minus 1. But notice that if I consider each one of these, do you notice that when I go through each one of those, I'm going to examine L sub I is equal to X. So notice, so this is the invariant here, is after. So suppose I look at one iteration of this, say some value of t that's going to occur for this loop. After t iterations of the loop, found is going to be set to be true. So found is equal to true. So it's actually set to be true. Now I must stress that this I literally mean it's equal to it. It's set to be true if and only if. That means whatever is going to be right here follows if and only if. As in, if this is the case, then whatever's going to, I say after if and only if will also be the case. If this is not the case, then whatever's going to come after the if and only if was also not true. If and only if x is in L sub 0 all the way up to t minus 1. So if I look at my iteration, so after this iteration, so for example, after the iteration, after say one iteration, what this is saying is that you've checked L sub 0. That's it. That's the only part of it you've examined. But after 2 iterations, you'll notice that I will have examined L sub 0 and I've also examined L sub 1. Does everybody see that? So if you're wondering, this is going to be going over the following range. So keep in mind, remember that if we have it where we have no iterations that have happened, it still has to be the case that it's false, right? So keep in mind that this value of t, it ranges from 0 all the way up to n. So when you plug in t is equal to n, then you get 0 to n minus 1, right? And that's exactly the kind of thing you're looking for, right? Because when this finishes, you've had to have examined all the positions. Keep in mind, you can easily modify this algorithm so that you just exit when you have everything. So the meaning that you got the true result. So this is the big piece that makes this work. Now, you might say, Dan, that's pretty nice, but how exactly do you prove that that is actually the case? So let's talk about this. We're going to prove this using the principle of mathematical induction. So it's going to eerily remind you of the actual algorithm's execution. But it is not the same thing. It will make you feel like that's actually that's happening. We got to check that condition. So to prove the correctness of the algorithm, if I can prove this property, then we're done. Does everybody see that? Because this algorithm over there runs in finite time. Linear search runs in finite time. You can prove this by arguing quite simply, hey, look, notice that every line of our algorithm finishes in a constant amount of time except for that loop. So notice that how many times does the loop perform iterations? Well, it performs exactly n iterations for that loop, which is a finite number. So the whole algorithm has to terminate in finite time. So this is the key part for the correctness, meaning it's going to output correctly. Because you just simply plug in when t is n, right? And that matches up when at the end of that execution of the algorithm, right? So if we have that, then we're all done. That's all we need. So I'll have more details if you ask me about them over on the subscription-based approaches we have here for like Patreon and that. If you ask me about this, I can provide you the notes for this proof. Okay, so let's try proving this. So to prove the correctness of the algorithm, remember, to be clear, what it means for the algorithm to be correct is that for every instance of our search problem, so every one of them, the array, value, length, I gave it to this algorithm. This algorithm has to produce correct output, so it has to present me an answer for every single one of those instances and has to be correct, meaning the output matches the solution. So, let's see. I was about to say, to prove the correctness. So I'm getting really excited here. To prove the correctness of linear search, for any positive integer t, let S of t be the following. It's going to be this statement right here. So for the sake of clarity, I'm just going to tell you to just look at that statement. That's going to be what S of t is. Hopefully that is clear. So that's just the statement, is that we're going to prove the correctness. We're going to we're going to let this statement be the invariant that we have. So next, that means for my induction, I have to first kind of make sure that we walk through all the steps to apply mathematical induction correctly. So the first thing I have to do is I need to start off with our base step. That means I'm going to have to come up with some of the simpler, smaller cases, so that will be big enough to allow me to prove for any arbitrary rung of my claim. So I could take one rung, go to the next rung, and I should be able to use this to prove every one of the steps in between. So you can think of, say, for example, Miss Kitty the cat trying to teach Miss Kitty how to climb up to the top of a bunk bed by showing the cat to hop one rung and then maybe two rungs, but then taking the cat and showing arbitrarily two rungs and showing how you can go from one rung to the next rung. And the whole idea is that we formulate an argument that uses the previous rung to help you prove the next rung. So I have more discussion about this elsewhere on the channel. So I recommend, if you're curious about that, feel free to reach out. So anyways, let's talk about the base step. So we got to start with the first. I must stress that I'm going to try to keep this rather straightforward or brief. If you want the full proof, bug me for it. You'll find I'll be able to produce it for anybody subscribed to my support network. So anyways, so to prove S of 0, we must show, because what's the claim? The claim is if it's S of 0, actually, is it for any positive integer? I think it's for any integer t. Yes. It's not positive integer. We want it to be integer t greater or equal to 0. That's what we want. Yeah, that would make more sense with what we said over here, right? So we must show. Sorry, I'm getting really excited because I'm trying to do this with you guys. So we got to come up with this together. That's the big thing. We must show. So I must stress there's a very large element of improv when I do a lot of this stuff. So we have a lot of fun. So we must show that linear search sets found equal to true if and only if, I'm going to abbreviate if and only if with IFF like this, if and only if element X is in the following range. It's in this subarray, L sub 0 to -1, which I must stress that this is an empty array. Well, what's the thing? This array that I've written here, because notice that the starting index and the end index, this is the end index, is less than the starting index. So there's no elements here. So surely X can't be in any of this, right? And this is also the case that notice that that 0 iterations have happened as well. So keep that in mind. So just to keep this brief, so observe that X is not present as L sub 0 to -1 contains no elements. Right? So what does this imply? This implies all I have to do it now at this stage, because we know there's no elements at all, right? That we can look at. So all we have to do is show that found is not true. That's all I have to do. So all we have to do is show that found is not equal to true. But what did we say earlier? Well, let me put a star beside that. Notice that found is set to false at the beginning. So if x is not found yet, found is not updated. But notice that no iterations have happened yet. So this has to be true, right? So I'm going to say by star, found is false, proving S of 0. Piece of cake, right? That it almost feels like I'm cheating, right? It's like there's no iteration, so I obviously cannot have it, so it's true. But notice that this is because of the way I described the algorithm to you. Does everybody see that? So that brings me to talking about the actual induction. So that's the part that's really fascinating about this. And it will feel like what I did here. So every time I examined an element, I extended how much I knew about whether x is in the array or not. But keep in mind, like I said, x may appear several times in the array. The point is it's a part of the subarray. So every time I do an iteration, this expands out by 1. So if we think about this carefully, every time I consider the next element, it's almost like I have all of these ones here already, and I'm just extending the range I have by 1 after one iteration. So perhaps I can use that information to help me prove what we call the induction step or inductive step. So let's do that. So another way you can look at this is, instead of thinking about it in terms of the entire array, just think of any one step in the array when we consider linear search. And this is what I was suggesting is more a rigorous way of thinking about this. Is that each time I do one of these iterations, well, you already have, like say for example, I'm going to consider this one in the current iteration. Well, it means I already looked at all of these, right? So whenever I consider the next one, okay, there's this plus all of this that I've now considered after that iteration, right? So let's kind of put this into words. So given S of k, I'm going to show you that S of k plus 1 follows. So if S of k, then S of k plus 1. So we're going to fix some k greater than or equal to 0, because I want to have the first rung in there. So the biggest rung I initially climbed up to, and up in this case. So I'm going to fix some k greater or equal to 0. And then we're going to assume that S of k holds. Now I must stress, when I write out S of k, what I'm saying is everywhere in this statement you're going to put k. So we're going to assume that S of k holds. This is what we're going to call our inductive hypothesis or induction hypothesis. So I'm going to abbreviate this as IH. Comma, so that we can prove, sorry, my we is just melting here today, so that we can prove S of k plus 1, which I'm going to write this out because I think it's rather important for you to see it. So after k plus 1 iterations, iterations of the loop found, I was about to write false, found is assigned to be true if and only if what? What is it? That x is in this range. L sub 0 all the way up to k. So it would be positions, so box 0, box 1, box 2, all the way up to box k. Notice the indexing. So please take note of that. And I'm not just trying to prove this. I'm trying to show that this follows. That's an important part of this. So I'm going to show you that if S of k, then S of k plus 1. So I'm going to use S of k to help me prove S of k plus 1. Because if I know what S of 0 is true, and I could show you from arbitrary rung to go from S of 0 to S of 1, then the same thing should be able to tell me, the same part of this proof should be able to show me how to go to S of 1 to S of 2, S of 2 to S of 3, S of 3, S of 4, and so on to any arbitrary step to sufficiently needed size. So in our case, we just want it when we have S of n. If we have S of n, we're done. So I want you to observe that there's really only two possibilities that can happen. So the first possibility is that x is in fact in this range. But it's not just in L, it's not in this range entirely. It's not like all of this. It's actually only a part of this. It's all of this up to the previous position to this one, akin to what I drew in that rectangle over there. And this one right here. Suppose that I have all of this, and suppose I tell you it's right in there. Suppose it's in there. Then, well, what does that mean? Well, this range it's saying that if S of k, so remember S of k tells me after k iterations of the loop, found is true if and only if x is in this range, but k is k minus 1, right? Notice it's the same one right here. But what does that mean? If this is the case where it is in it, then it most certainly, the algorithms, the induction hypothesis is enough to get that. Then by the induction hypothesis or inductive hypothesis, after k iterations, found is assigned to be true. So found is equal to true at that stage. But one other thing I need you to notice, if we go back to the algorithm over there, did you ever see me reset found? Found never gets reset. So as soon as it becomes true, it always stays true. So I'll say variable found is never reset to false. False. So after k plus 1 iterations, found is still going to be true, as desired, right? Because so what I'm trying to do is I'm trying to show you that if I know what happens with the first k iterations, so after the k iterations, I want to show you that the algorithm still is correct after k plus 1 iterations. So if this happens where x is already in, say, this box right here, so this is like your k iterations, after k iterations you get this. If you want that one extra one, what I'm saying is if it's already in here, notice that it never resets found to true. Sorry, found to false, my apologies. Then that means that it's always going to be that it stays true, even when I go to this one, even if it doesn't actually match it. So if x is in here, it's going to set it to true right about here, and then it will never change it from true. So that's how we know that we're okay. Analogously, this would also say to us that if we don't find x yet, then it's still false, right? But right now we're trying to see if it's in there. So now there's only one other possibility that could happen now. Suppose that now, so we know it's in this range, but what if it isn't in this range? There's only two possibilities here. It's either in this range or it isn't in this range. If it isn't in this range, there's a possibility that x could be right here or it could not be. That's really the natural thing to think about here. So x is not in L sub 0 k minus 1. So we just have the same thing. We can just use the inductive hypothesis or induction hypothesis, and this will feel like you're just executing out those iterations because of the nature of the claim. At least I like to think of it like that. After k iterations, found is still false, right? So found is equal to false right now. And there's only two possibilities that now remain for this case. It could be that x is in the next spot, or it's not. And if we can figure out what happens in those two cases, then we're good. We're good for this induction step. And instead of n, let's say, so let me reiterate. X is not in this range by the induction hypothesis after k iterations. Found equals false. Actually, let's put the and back in. And after k plus 1 iterations, either L sub k is equal to x, or L sub k is not equal to x. That's the only two possibilities after the k plus first iteration. These are the only two things that can happen. So all you have to do at this stage, I'm not going to write it here, but consider the case when L sub k is equal to x. If it is, what it will do is the algorithm will set found to be true in that step, which will give you as desired that we have for our invariant, right? It says that, so if this is equal to x, then it's saying, so the algorithm will set found to be true in that case. And as we've established in all those other spots, it wasn't there, but it's in this spot because we've considered this possibility. If it isn't, then we know that found is still false because of what we just said right here. So it's still false. So it still remains false, which also is what we need and is required by this claim, right? This says that found is set to true if and only if x is in that range, but it isn't in that range, so x is still false, because that's the only other possibility. So this would, with these two things together, so I'll let you think about that one part there. So I'm going to put some dots here. So I'll say thus completing the inductive step. And now once you have this, you can now use the principle of mathematical induction to prove the correctness of the algorithm. So all we have to do at this stage is you plug in, so you use the principle of mathematical induction to prove this invariant holds for all the values we've talked about. And in particular, you just say, okay, well, if it's true for all of them, then consider, because we have an array of length n, then consider S of n. And in S of n, that is when you consider all of the elements, right? And then the linear search algorithm is correct. And that's how you'd finish off this proof. That's pretty sweet. So one last remark I wanted to make, because I haven't talked about complexity at all. I thought I would measure the time complexity of this algorithm with you. So you can look at this proof as some parts of it I would encourage you to fill in. So it's more of a thing where we had fun doing it together. But let's talk about the time complexity for linear search now. And I must stress that there's several ways to describe linear search. This is one variant of it. You could easily have it where instead it returns a position, or you can also even have this one change where it actually exits out this loop using a so-called break statement. You could even have it return at that spot and say return true. The way I designed this algorithm for you was to deliberately make it so it's easier for me to prove this invariant. Once you have this invariant, it shouldn't be very hard for somebody to be convinced that any one of those changes won't change the correctness. So, that being said, let's talk about the time complexity of this. So notice that if we look at this algorithm, we already established this terminates in finite time, correct? So all I need to do now is measure how many operations are happening. So there's this return statement, there's this found statement here. These two together, they take some constant number of operations. We'll call them C1. There's C1 many operations here. Notice that this takes constant time, that takes constant time. Likewise, if I look at what's inside the for loop, evaluating and checking if this is equal to x, this takes constant time. And even if I had to evaluate this, would take constant time. So all of this takes some C2 many operations. So I must stress that we have to look at this in terms of the worst case, right? We want to know how much time is required to solve this problem, right? For our given algorithm, we want to know how much. So I've just measured out how long these would take with respect to the input size, which is what we classically do if we were trying to measure it in this way. So let's talk about this now. In the worst case, what would happen? What would happen? Let's think back to this issue around the boxes here. So let's think about the boxes. So when I did this, I swept all the way through from left to right. That's what this algorithm does, right? Well, what happens in the worst case is that x simply doesn't exist, right? That means you have to examine every one of the boxes, all of them. So in the worst case, scenario, which you need to identify these instances, the ones that cause the algorithm to take as long as possible, performs the most number of operations. If you could do that, then you know how long this algorithm requires to execute. So if x is not in L, that's the worst case, because this will now the way I wrote out this algorithm doesn't make any difference. But if you take any version of this where you simply have it where it returns here, or say in other versions, there's several other ways you could rewrite this algorithm. The point is that it does the same thing. It ultimately will still have it where it examines each one of the spots. If it finds it, it will tell you, yeah, there it is. But the point I'm getting at is that these are all different ways of describing the same process. It's just I did something deliberate here to make this easier for us to understand. But if x is not an L, notice that this will never set this to true, meaning that regardless, even if I try to put shortcuts into this algorithm, meaning I make it so it returns found right here if it gets a match, even if that happens, if x is not an L, it would force it to do every iteration of this loop. But for our version here, it wouldn't matter. It always will do all the same number of operations. Hopefully that is clear. Regardless, I like to identify a scenario where this causes the most number of operations. But here we go. How many iterations happen here? Complete iterations. Well, n of them, right? So I have n times C2. So if I put this all together into a complexity function, the complexity here, now keep in mind there's several ways you can count this. This is just one such way. You'll end up with the same complexity function if, for example, I counted them by operation count, or I counted the extra iteration of this loop. It does, like if I was doing the conditional check for the for loop, for example. I would get C1 plus C2 times n. And if you look at this very quickly, this is a linear function. This is a linear function. This runs in big O of n time. In fact, it runs also in big theta of n time as well. In fact, you can also show that on average, if you were to add that shortcut in where you exit out right here, Even on average, in the average case, where x may be appearing on uniformly, there's a possibility of it appearing in any one of these spots, it still is linear time. I will not prove that here. So that's linear search. Isn't that fascinating? Okay, so let me see what's going on over here. So don't be shy. If you have any questions, I'm happy to answer any questions. Hopefully everybody's having a good day. I know why I'm having a pretty good day. It's busy, but we're having a good time. Yeah, that's linear search. Isn't that kind of cute? So this is, oftentimes, this is a pretty common like first algorithm that you would learn. So I thought I would do this by explaining it in this way. So I'll just make a note here that it doesn't really matter. So that really matters if you exit right there. But yeah, no. What I'm going to do is I'm going to erase the board back beyond here. Blah, 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 blah. I'm sorry, getting very excited here. I will erase this board behind me because what I want to do next is I want to convince you that linear search is actually an optimal algorithm, meaning that it matches actually the best known lower bounds we have for solving this search problem. One where we have no knowledge about what we need to do. Linear search will cover it for an array like this. So let me just erase the board over here. If you have any questions or anything like that, don't hesitate to ask. So this is where it's going to get a little bit more advanced. So you're going to see that I'm going to kind of keep this kind of going where we're going to have it where I cover one algorithm. I'm going to cover a lower bounds discussion about it. And I'm going to cover another algorithm. So in this one, I focus primarily on the correctness. In the next algorithm, after I cover this first lower bounds result, I'm going to focus mostly on the complexity of the algorithm. The correctness, if you bug me, I can give you the proof of correctness. It's actually also in my book, Advanced Data Structures. You can find a proof of correctness there. You can easily augment it to make it into an induction proof using an invariant similar to this one. Just it's a little different. It just requires you to check and observe, oh yeah, there's an interval or so where the value that I get, it's always within some value. But if you're curious about that, reach out to me. So we're going to be using these boxes to help us explain this discussion about lower bounds. So this is going to play a big role in the next part here. Because I don't want to get too overly crazy when it comes to the formal aspects of this. Instead, what I would like to do is focus primarily on you understanding like the main idea underneath it so that you don't feel like I'm giving you too much baggage when it comes to theory. Instead, I want you to focus on the big ideas. Excellent. So I'm just seeing where we currently are in our discussion. Okay. I'm just checking on one thing. I'm looking forward to talking to you about this stuff. Sorry, I'm getting very excited here. Okay. Okay, so we're going to be talking next about the lower bound for the search problem. So let's get into this. So anyways, everybody, we're going to be now talking, sorry, very excited here. I always get very excited when we start talking about computational limits here. So previous to this, we talked about linear search. We talked about a proof of correctness for linear search, and we established that that algorithm runs in big theta of n time, or big O if you prefer to talk about it in those terms. It runs in linear time. Now, it would be nice to know whether that algorithm is going to be among the class of algorithms that are the best known ones to solve the search problem. Now, remember, in our problem, we're just given a set of elements. So in our case, we thought of it as just an array. We have no previous knowledge about what's going on inside of here, right? I must stress that the arguments I'm going to be making here are rather general for some things, but the big point is that we sequentially check each one of these to determine if a value that we're given is in one of the spots. We want to know if it is there or isn't there. So to do this, we're going to be establishing an idea of a lower bound. So just to give you kind of a big view of this. So we're going to talk about lower bounds. So consider this more of a high-level explanation. If you find yourself curious about us doing more of a delicate exposition into this topic, please just let me know. I'm always happy to go exploring this. So very often when we talk about a problem, so suppose I gave you a problem that I would like to solve. So a computational problem specifically. So I give you some problem. Each of this consists of different problem instances. We feed these to an algorithm. And we say that the algorithm is correct if for every one of these instances it produces the solution, or thus the optimum, or whatever it might be for the given type of problem. So what we like to do is we'd like to know what's the most efficient way to solve the problem. Now, that's a very broad question. It's very hard to establish if we actually have the best known algorithm. It's a very interesting and fundamental question. Especially that we're given our search problem is where we're given a collection like this where I don't know what's inside of here at all. So I must stress that we have kind of two concepts. We have the idea of an algorithmic upper bound. So an upper bound. So this would be the time complexity, or whatever complexity you're curious about. So in our case, usually think of it as time complexity, the worst case time complexity. So the time complexity best known to solve the problem. So this is some algorithm that we have. So for example, if I were going to consider like our search problem, this might be perhaps, this is linear search. In fact, it is in this case. So linear search in our example with the search problem would be, and provides us an upper bound on how efficiently we can solve this problem. So likewise, there's this concept of a lower bound. So this is the required time to solve the problem. We'll say required time complexity to solve the problem. There's a lot of these discussions when it comes to different types of problems. So sorting is one where this very often comes up when you learn about some of this stuff. Searching is another one, so I'm going to focus on that. So you know when the problem is essentially solved, or at least you can start narrowing it down even further, once the upper bound and the lower bound are the exact same, or at least very close to each other, and there may be a pretty good reason why they can't be. Or at least we lack the methods to do so. The point is that it's a very interesting research question. If you can get these two to be equal to each other, you could basically close the book and say the problem solved, right? You can't make it go any faster. However, after that stage, there may be further refinements you might make. For example, the problem of sorting has been, in this sense, solved for decades. But people still keep talking about sorting algorithms because it's a very fundamental question, or a fundamental problem that computer scientists and generally people that like to sort data might want to have. So there's a lot of different sorting algorithms out there that even then, some people came up with these kind of results. Well, the thing is you could always narrow what exactly you want the sorting algorithm to do, just like you could do the same thing with the search problem. So in our case, we're going to be considering when we have an array, we don't know there is nothing we know about what's going on in here. All we know is that they are going to be equal to the value, or they're not going to be equal to the value. So, that being said, let's talk about this. So you might ask, Dan, how the heck do you prove this? Like we know we could present an algorithm, analyze its running time, and if it's the best known one we currently have, then it falls under the UB category, the upper bound. So it's like an algorithmic upper bound on how efficiently we could solve it. Likewise, lower bound, well, what can you do? One thing that you're going to notice very quickly is we cannot make assumptions about too many things, right? Those assumptions will limit our results. So the big thing is that we cannot assume one specific algorithm, right? That doesn't tell us the time required to solve the problem. We can introduce other constraints, for example, that might be interesting. For example, say one that will come up in a little bit is like, oh, well, suppose that the array is sorted. And suppose that the elements have a special property where you can compare them, say one's less than the other or they're equal. These are specialized assumptions that we can make to help us better understand how we can solve the problem. But notice that I'm not making any assumptions about what the algorithm is. I cannot make assumptions about the algorithm. I can make assumptions about perhaps what the algorithm is capable of doing, for example, but not specifically what the algorithm, like one specific algorithm, because that doesn't ultimately tell me a lower bound on how efficiently we could solve the problem. But here's the thing, when you break it down to a class of algorithms, like based on what computations it's allowed to do, then you got yourself something, at least a good starting point, so that you can ask natural research questions from there that either could generalize those research questions or they might be more narrow, which is a very natural place for a lot of this discussion to go. So this brings me to talking about what we're going to talk about here. We want to establish a lower bound for the search problem as we defined it previously. So one way to do this is by using what we call an adversarial argument. So you might ask, Dan, what do you mean by an adversarial argument? So I must stress that the way I'm going to introduce you to this is going to be somewhat informal, but I'm hoping that by the end of this you'll get kind of the gist of the idea. Like I said, if you're curious more about this, I'm happy to talk more about it in a future video. So I must stress before I get into this. Sorry, I'm really bumping this up. You got to think of this adversary as something imaginary. It's something to help us craft a discussion around what if we give you any one algorithm, can you give me an instance that will always cause a given algorithm to perform as many operations as necessary to establish a lower bound? So it has to do at least this many things for any one algorithm under our presumptions. In our case, we're just checking if they're equal or not equal, which I think is a rather it's a very, very basic kind of assumption that you can make for our problem, because we need to know if it's in there or not. It's kind of integral to the problem itself. So I must stress that this adversary, there's a lot of ways you could think about the adversary. There can be different kinds of adversaries, like based on what they do and what they are capable of doing. So I must stress, however, this is an imaginary concept, just to make it easier for us to think about how we can construct instances that always will cause the algorithm to perform at least some number of operations. Hopefully that is clear. So you got to imagine it like I give you an algorithm. So suppose we have an algorithm that asks questions. So you can think of these as guesses about the input. And remember, we are not assuming any one algorithm. This is going to be where we just presume it's some algorithm. It makes guesses about the input. So in our case, this would be very simple. Is X in the array? So naturally, one way you can do this is you can ask, is X in this box? Is X in this box? Sorry, I'm just dying by the excitement of this. Is X in this in this box? X is in this box. These are guesses. That's what I mean. It's a bunch of questions we're asking. Now, this is where the adversary comes in. So suppose that this adversary can craft for each question a worst possible answer to the question. A worst possible answer to the question. But here's the catch, though. The adversary can't just make up anything. The answers have to make it so that it's at least going to give you one input, or i.e. problem instance of your given problem. So it's going to craft an instance. It's going to make one out of these guesses. But so it has to be consistent with one problem instance at least. So you can't just make it so it makes up something that the algorithm would never be attempting to solve, right? It has to be consistent with one input. So the answers must be consistent. Sorry, my writing is just melting today. Must be consistent with one problem instance. So here's the catch. Imagine you're playing a game with somebody. Suppose you're playing, I'm not sure if you've ever heard of the game called Battleship, for example, or another game called Mastermind. In these games, the way it works is that you have somebody you're playing with. It's like a two-player game. Suppose you give me the idea of Mastermind. So Mastermind is a game that works like this. Now, it may have different names. It has some pegs. And they're hiding behind some guard. And the other player, this would be you playing, you have to guess the color pattern of these pegs that go into these holes. So you put colored pegs in, and if it matches the pattern, what happens is that information will get revealed to you. But the thing is, you get a certain number of guesses, and this player wins if you don't guess the pattern. So say, for example, this one's a black, this is white, this is black, that's white. Suppose that I put a black one here and say a white one here, but I put two blacks. That's not a correct guess. The player I'm playing against will tell me how many I got correct, but they won't tell me which ones. Well, you can imagine this like in our concept here. Suppose that this adversary has the ability to know the order of your guesses because they'll know about your algorithm. So what they could do is they could craft an instance for your one given algorithm, which, remember, like I said, you can't presume any one specific algorithm. You presume have basic assumptions based on the type of algorithm. By adding more assumptions, you restrict the possibility of your result generalizing. So suppose you have these guesses. Every single time, suppose that this adversary, every time you made a guess, you can almost imagine it like the adversary has the ability to know what you're going to guess next, so that the adversary can switch around these pegs without you knowing that you're about to make a guess. But the adversary will know how to switch these pegs around so that you keep guessing until you get the very last guess. And then it will say, hey, look, you got it. But the thing is, the adversary is essentially cheating, but cheating enough that they're cunning enough that they'll give you something that's consistent with an instance that the algorithm would have to solve. So this is a little abstract at first, but here's the idea. The adversary is going to build an instance, and then you look at what this instance does, and regardless of what the algorithm is. But the whole idea is that this adversary is going to be malicious. It's going to try to cause the algorithm to perform as many guesses as possible in the worst case. So it's going to try to get it so you have to perform at least a certain number of guesses in order to solve the problem instance that gets crafted, regardless of what the algorithm is. So hopefully you get the idea. So I'll show you an example of what I mean by this. So I'll give you the formal idea behind this. So here's the formal idea. We will show for every algorithm A and input size n, there is some input. So this will be selected by the adversary. That's the kind of the imaginative part about the adversary. Input of the problem of size n, where A takes at least L of n operations, where L of n is the lower bound. So whatever we try to make L of n as, or this function L, we want to make it so that it is as large as possible. So we want to make this lower bound as large as possible so that we can get an idea of how efficiently we need, like how much we have to do at least. So if we can make that at least as big as possible, then it gives us an idea of how much work we need to do and see if we can come up with an algorithm to match that. If we have a very poor lower bound, it may not mean anything significant for us because we just lack a good technique to prove it. So this is a theoretical concept. Just be clear. We're not talking about one given algorithm. We're talking about any one algorithm requires this. So under the presumptions I've made. So in our case, we're going to presume that we know it's either equal or not equal. So that's a pretty broad generalization. So one algorithm I gave you already is linear search. So I just wanted to remind you what linear search does. So remember, linear search is just one algorithm. There can be other algorithms too. So something I wanted to talk to you about, to just kind of make this adversary concept a little bit more clear, I'm going to use our boxes over here to help explain this idea to you. So you got to imagine this. When you give me one algorithm, often I want to know how long it's going to take to solve the problem for any one instance of a given size. So for example, linear search takes big O of n time, right? So what did we do to establish that? Now, in our way I wrote linear search, it made it easier for us to prove the claim, but you could have easily showed that if I wanted to make it so it exit out of that loop much faster, I could just simply have a return statement inside of there and just say return true when I find it, right? Well, in the worst case, it would just simply be that X isn't in the array, right? Well, in linear search, what we do is we scan from left to right, go position by position, and we check inside of each one of these and we see if it matches X, right? See, here's 6. If X was 6, then I would have found it and my found would be set to true. I would know that it's in there and that'd be all I need to do. Well, in the worst case scenario here, I want to have it so X isn't in here so that I go through all of these boxes, right? Well, I don't know what order my algorithm might actually do them in. So for example, I could give you another algorithm, for example, just like linear search, that goes through all the elements from right to left instead of left to right. Suppose instead what it does, perhaps it may even go this position, maybe go into this one next. Sorry, that was a little loud there. So it goes into this position, then it goes to this position, and then it starts going through all the odd positions. Well, actually, these would be technically this would be even, odd. Yeah. See, the numbers are right on the boxes. So we need to keep in mind that all I have capable of checking is x is an L, as in x is equal to L sub I for some position, or we don't. So I don't know what order the algorithm would even examine these. It may even not even examine them at like all just one by one, right? So I need to keep that in mind. So what I'm going to do is my adversary is going to come up with a way. So suppose, for example, suppose that I was given an instance where I given the array L, a value x, and n for the length of the array. So for example, suppose that I always give it a value that is not in the array. Always. Well, regardless of what order you actually examine these in, it will never equal the value x. So what I need to do is every single time I'm going to construct the instance. So when I build the instance, I'm always going to make it so that it never will eventually find this value x. Or, even better, if I want to make this even more playful for the adversary, what I could always do is just make it so that it just simply finds x in the very last spot every single time. But the thing is, once I know what the algorithm, what order the algorithm checks, whether they're equal or not equal, then I could just simply craft an instance that will have this behavior, regardless which algorithm it is. So that's where the adversarial argument really goes from here. So let me sketch out this with an adversary argument. So here we go. So let's prove that the search problem, when I'm given an array and I don't know anything about what's going on inside of it, except for I could check if it's equal or not equal, I'm going to Okay, I think we're back. I think we're back. Okay. We had a little bit of a technical issue there. I'm just going to make sure I got things straightened out here. My apologies. One of our cables got a little loose there. Just going to make sure I got everything sorted out. Let's see. There, I think that's better. My apologies, everybody. We had a little bit of a technical issue there. Okay, we don't want it that far. No. Get to see a little bit of the magic behind here. Okay. Here we go. Sorry about that, everybody. We had a little bit of a technical issue there. Yeah, no, one of our cables sort of got loose on one end. The cats were playing around a little bit out here. So let's get back into here. My apologies, everybody. So, anyways, where I was. So, reminder. Remember, the goal here is for our adversarial argument is to craft an instance, regardless what the algorithm is, that will require it to perform at least some number of operations. So here's a theorem. So given an array L of n elements, the search problem cannot be solved in little o of n time. So I mean worst case time. Another thing you might ask is what the heck is a little o? So the little o is, so you know how in big O we have an asymptotic upper bound. Now this is an asymptotic upper bound too, but it is a strict upper bound. So that means that this is saying, so this will consist of all the complexity functions that are not linear ones, but it may consist of the like logarithmic functions, constant functions, but it will not contain the linear ones. It has to be all of them of order less than n. So another way you can rephrase this is saying is it requires what we call big omega n operations. So here's how the proof's going to go. So here's how the adversarial argument will go. So suppose algorithm A, so I don't know what algorithm A exactly does, it just solves the search problem. That's all I know. That's all I know, guys. So the order A examines elements. Now I must stress that these are just the order we examine the elements. It may not be exact, like they may consider multiple elements over and over again, but these are the order the elements are first considered, okay? It examines elements is as follows. I0, I1. So these are a whole bunch of indices or positions for an array. Like I said, these could be potentially visited more than once by your algorithm. The point is that this is the order that they get examined in by first appearance. So construct, and this is what the adversary will do, is construct array L so that L sub I0, L sub I1, all the way up to L sub I n minus 2 are all not x. But L sub I n minus 1 is equal to x. So So if this happens, right, this is the order that they're considered in. So if all of those are not X, that means that you have not found X in L. However, by the time you get to the last one you've first revealed, that is X. So keep in mind, this is one such way you could build an instance regardless of what the algorithm is. So A examines, because how many indices are there? N of them, right? So A examines N elements regardless. So the point is that it's at least N. It has to examine N of them. Regardless. Therefore, at least big omega of N comparisons are required. And that's the end of the proof. End of the proof. So, talking back to our discussion about upper bounds and lower bounds, notice that this claim is saying that you cannot solve the problem any better than linear time. That's what this is saying, in plain language. So it means that if you give me linear search, and linear search runs in linear time, asymptotically speaking, it's optimal with respect to time, right? Because that runs in big O of n or big theta of n, and this claim is actually saying that no, you can't do any better than that. So we could say linear search is the best known, well, it is among the best known algorithms to solve the search problem, right? So piece of cake, right? So let's head back over here. I just want to see how everybody's doing. It's a rather quiet day today. But that's everything I have to say about linear search. So what we're going to do now is I'm going to talk about binary search, and we'll talk about some ideas around binary search. And then we'll do the time complexity analysis for binary search. We'll see where we could go from here. So what I'm going to do is I'm going to erase all the boards, and we're going to get into this. Let's talk about this stuff. But by the way, if you have any questions, please don't hesitate to reach out. It's one of those days, even though it's a little quiet, I know that somebody might stumble across this and want to watch this later on, and they may have a very interesting question. So please don't hesitate to ask me questions. I'm happy to answer them. Oh man, this board is getting a little funky, man. Just erasing the board, Okay. I really should have used the other eraser on this board. Got a few streaks on here that are a little bit icky. So let's head over there. Before I do that, I'm going to make sure that we don't lose our cables. See, we had a little bit of a fun time there. I had to just check on things. Okay, let's try this again. I just want to make sure that we didn't lose anything over here. We had some technical issues earlier that I had to sort out. We sort of lost the feed for a moment. Okay, just please give me a moment. I'm just gonna readjust our camera because I am sort of a one-man person here. One-man Dan. That's sort of how I am. So I'm just gonna get this moved over a little bit there. My apologies. I don't like usually seeing all these other things, but It's one of those days. Let's see, cross our fingers it does not get jammed. It got jammed. Let's try this again. Okay, let's try this again. Let's try this again. I always have to make sure that we're not losing anything, okay? Okay. Okay. There. And let's see. Okay. There we go. That's better. My apologies, everybody. This is when you're doing this stuff live, you get all sorts of fun surprises that might happen. That's sort of the blessing and curse of doing things live, is that you only really get one chance to do everything. So it's sort of the nature of the beast when it comes to this. So let's look into this a little bit. Yeah, I see I can move this over a little bit more. Let's move this over a little bit more. Okay. Let's go a little bit further. I don't want to have it so that you're going to get all of this extra stuff when we never write over there. It's always this delicate process. Okay, let's go a little bit further. Okay, we'll go with that. Actually, no, let's move it over just a little bit more. Okay. Okay. One other thing I want to make sure I prep here is I want to make sure you're going to see a little bit of the secret that goes on behind the scenes here. Is I'm going to move all of these elements so that they're all in sorted order this time. So 2, 3, 5, 6, 7. So let's try this now. And that's pretty satisfying. Okay. So anyways, I'm just going to check my volumes here on my end. Okay. There, I think we're doing good. So anyways, up to this point, we've seen linear search. We've seen that linear search is the best possible, among the best possible algorithms we can obtain for the search problem when we have no information about what exactly, like, is it unsorted and so on. Like, we have a lot of things that we could possibly do from there. So what I'm going to be doing today is we're going to be considering, seeing as we talked about linear search already, and we've seen that it has this lower bound that takes linear time. It requires linear time to solve that problem. What can we do if we know actually more information about our input? So suppose I give you a case where instead of it just being any old array L of n elements, what if the elements are actually sorted? So it means that these elements are comparable, meaning that I can always list them out from smallest to largest. So this is going to be the big assumption I'm going to make. So just as an example, so when we talked about linear search, I talked about these n boxes we had, right? Here are just 5 of them. In here, I didn't necessarily know what I might get when I open up one of these boxes. However, here's an example of an instance that might look like. So suppose in position 0, I have a 2. Position 1, I have a 3. Position 2, I have a 5. Position 3, I have a 6. And position 4, I have a 7. So I have all of them, but notice that the value doesn't like dip down, for example. It always starts from smallest to largest. So they're going to be in non-decreasing order. So I'm just going to say, so we've seen how to solve solve the search problem, oh no, my little turtle friend fell. I'll help my turtle friend out in a little bit, okay? We've seen how to solve the search problem in big O of n time. We've seen this with linear search, right? And we also established that that is among the best known algorithms for solving the search problem. This is when the array is unsorted. So instead we're going to assume array L contains n comparable objects or comparable elements. So that means that you should be able to tell me if it's less than that thing, it's equal to the thing, or it is greater than the thing. So if I give you two numbers, for example, numbers are comparable objects or comparable elements. There's other kinds that you can have as well. There's many kinds of different kinds of data you can have that have this property. If you could do this, then you could say it's comparable. So, anyways, if you know it has n comparable elements and L is sorted in non-decreasing order. Keep in mind this is a rather loose constraint. You can always do the same thing but backwards if you need to. Note that if it's comparable, you could easily just flip these signs and you could change the ordering very easily. I'll let you think about that. So if you have this, do you have to go through the process that we went through before where we didn't know anything what's happening inside of here? No, right? I know that they're in sorted order from smallest to largest. So if I go through the same process I had before, if I just don't know what's in here, if I'm looking for X, sorry, that noise is very satisfying. I don't have to just guess right here and go sweep from left to right. Although that is correct, it most certainly will work. And it'll run in linear time. But normally when we try to solve problems, if we're given additional information like this, let's try to take advantage of that information. So instead of just guessing from here, say guessing sweeping from left to right, maybe we could do something else. So suppose instead of sweeping from left to right, we do something else here. So I have 5 elements in there. Let's see, we got 6. So we had 7. We had 6. We had 5. We had 3. And we had 2. Thought I would open those up again for you. So I have L, and I have 5 elements here. So their positions are 0, 1, 2, 3, 4. Now I can close this. So we don't need to know about these anymore. So let me just get my little turtle friend. There we go. So suppose that I have... Actually, no, let's go... I don't trust my turtle friend to start just sitting there like that. I'm gonna... There we go. That's a little better. Well, at least we got our little turtle friend hanging on out over here. I'm just gonna move this over just a little bit more. Okay, that's a bit better. So, anyways, we have our array L, and we know that they're sorted from smallest to largest in here. Now, like I said, you can always scan from left to right in this array, and you can indeed use linear search to correctly solve whether X is in the array or not. So for example, if I was looking for X is 8, you'll notice that it's not in here. So you'd examine all of them if you're using linear search. But here's another thing. Do you notice that 8 is actually always going to be to the right of 7? Do you see that? Likewise, if I had X, say another problem instance, if I had a 1, notice 1 isn't anywhere in here, but you know that 1 would always be to the left of 2 because it's sorted, right? Likewise, if I was looking for a 4, is it going to be anywhere? Is it going to be over here in the array? No, man, it's not going to be to the left of here. It's going to be somewhere between 3 and 5. That is something we know because it's sorted. So that brings me to the main idea I'm going to present here for you is what we call binary search. So instead of performing our guess here and sweeping from left to right, like we did in linear search, we can do something a little bit smarter here, okay? So instead, suppose that I try to cleave this array, not literally, but figuratively. I would like to have it so that when I make a guess, I should be able to tell you everything to the left of me is less than me, and I may consider going left, or whatever I'm looking for may be bigger than my element, so I have to go right. So instead of it just being where I sweep from the left, maybe I should start in the middle. That may be a good place for me to start. So suppose I start right here. Suppose I make a guess that's right here. So you might ask, Dan, what exactly and where exactly is that? So suppose I have 2 bounds. I have a lower bound, like 0, and an upper bound guess of n minus 1. Now, suppose that I wanted to guess a position. Suppose I guess L plus U divided by 2. This will be about the middle. So I'm just going to round that down. This is floor. These are floor signs. It means round down. So for example, if you had a number like 2.5, I'm going to say make it a 2. If it's 2.8, make it a 2. If it's 2.9, make it a 2. Okay? That's what floor means. This is the floor function. So this will give me a middle position. So for example here, if n is 5, then n minus 1 is 4. So that means I could have 0 plus 4 divided by 2. So I have 4 over 2, which is just 2, right? That puts me right here. Likewise, if I had, say, 6 elements, it would be 0 plus 5 divided by 2, which, although I'd have an even number, I would need to pick some side to be the middle, so you'd go to the left of the middle in that case. So notice here, I start here. Notice that this is not 4, right? This does not equal 4. So do I need to go to the right at all? Is there anything over here that might get me 4? I want to know where it is. Nah, man, I don't need any of that. And you're not going to find 4 over there. You may find it over here, though, in this stuff. So notice that I've examined this position. There's no match with 4, so I know this position and anything to its right is out of the question. It's not going to be there. So now, naturally, what should I do? Well, what I could do, quite simply, is just make another guess. So you can think of this like a guessing game. You can use this strategy, by the way, if you think of a number sequence and somebody guesses a number for you, you can use this strategy to improve your guessing game to try to make it so you reduce the number of guesses you make. So if you ever find yourself playing a game of hot or cold, or guess what my number is, and they tell you it's either smaller or bigger, if you use this strategy, you could reduce the number of guesses probably for your strategy. So here we go. So suppose that I did this again. Well, notice that if I try to guess over this, I may guess this one or this one possibly. The point is that once I'm in here, I can check if 4 is there, and I can repeat this process over and over again. So in this case, notice that in here, I would examine this left part, or what we'll call colloquially the left half. In this left half, I would go in there, and I would apply the same process. Now, what I would do is I would apply it over the lower bound. The lower bound still stays 0 because I want that left half, but this changes from n minus 1 to 2 because I already guessed that. But is it really just 2? No, it's not just 2. It's 2 minus 1 because I already examined position 2. There's no reason for me to look at that. So then I look at these 2 spots, then I make my guess again. So my guess would be right here. 0 plus 1 divided by 2. So I have 1/2. Round that down, it's just 0. So I guess here next. That's not equal to 4. There's nothing to my left, right? But I don't have to look at this anymore, so I consider my right half. My intervals will change. Notice that now I'm going to bump this up by my guess plus 1, because I'm not going to check this spot again. And then I check it with 1 and 1. So notice that my guess will get me 1 plus 1 divided by 2, which is 2 over 2. That is just 1. That gets me right here. Notice that this is not equal to 4. And thus, what I do is, it's definitely not here, but 4 would be to my right, right? But you'll notice very quickly there's nothing there, right? But the thing is, I'm going to go to my right, so I'm going to make it whatever my guess was, plus 1. So I'm going to make this 2. But notice that these two numbers crisscross over each other. This is supposed to be a lower bound on my guess. This is supposed to be an upper bound on my guess. But notice that the lower bound now exceeds over the upper bound. This is what we call crossing the interval. They cross over each other. This means that there's nothing else left for me to check. And thus, I can tell you right away that 4 is not in this array. And this is what binary search is all about. So it's just playing a guessing game. That's all. The main thing that we're using is the fact that we know that the array is sorted. That's the big thing we're using here. So let's write out what this looks like. And I must stress that this is a very naturally recursive process, where every time I make a guess, notice that every single time I do the same exact thing, except on a smaller subproblem. So this is a very natural thing for me to describe using what we call recursion. So I want to take a problem, I want to solve a smaller part of it, so I describe this process in terms of myself until I get a sufficiently small enough problem that I can easily solve. So that's how I'm going to try to use recursion here. This is what we call a divide and conquer approach. So you can almost see this cutting out, where every time I cleave it, I always discard roughly half. So here we go. So here's the algorithm. So we're going to call it binary search. We're going to have the array L. We're going to have a value X. We're going to have L and U. Now, as I sort of alluded to, actually what I alluded to earlier, you're going to, when you initially call this, when you start this algorithm, what you do is you would assign L and U as follows. You would assign L to be 0, and you would make U n minus 1. So that's what you would assign initially L and U when you start this process. So I've deliberately written like this, even though it doesn't fit the same problem specifications, because you can easily rewrite this algorithm such that you have what we call a driver function that will call this with those two initial values in there. So there's the input and the output. Make sure you always state this stuff. It's got to be very clear for your reader. We have array L. And I must stress that this is a sorted array, so it means that we're considering a special case of the search problem. We have a value X, lower bound L, upper bound U. So these are lower and upper bounds on our guess. And this time I'm going to make it so it presents you the position. It's a position I such that L sub I is equal to X if X is in L, and minus 1 if X is not in L. So anyways, let's start getting into this. So the first thing did you remember how I stopped this process? So if I don't find the element I'm looking for, I don't find X. Well, this would be happening when the intervals cross, right? When L becomes larger than U, meaning there's no more elements to look at. So if L is greater than U, then we're going to return -1 because there's no more elements to look at. Otherwise, we're going to make our guess like we did over there. We're going to assign mid to be our guess. This can be L plus U divided by 2. We round it down. One tip I can give you about implementation is that if you're doing integer arithmetic, like a lot of programming languages, it will automatically round down for you, such as like Java or C++. At least at this time, those languages would automatically round this down because you're dealing with integer types. You have to be very mindful of this when it comes to languages that don't have typing like that. The difference between an integer division versus a regular division might matter, like in Python. If L sub mid, so we're checking position mid in L, and we see if that's equal to X, so I check in that box. If it is the case, then I found it. Otherwise, we have to examine either the left half or the right half. First, let's examine when L sub mid. So our guess currently is less than the current one, meaning that we have to go to the right half. So if this is the case, then we're going to return the result of doing binary search. So we're going to call binary search. So we're going to start this process up again with the following parameters for the inputs. So we're going to use L, as we did before, X again, except we're going to have mid plus 1. So we're going to have the lower bound, we're going to make it to the next position because we already checked our own, right? We know it's not equal to X. And then we have U's remaining unchanged. So that's your right half that you consider. Otherwise, you consider the left half. Otherwise, you return the result of calling binary search on the left half. LX. You would do this on L for the lower bound. We want to use L because we're going to the left half. But we already checked mid, so we're going to move it down by 1 position on the right half. Sorry, the right part of the left half. So this will be going on our left half. This is on our right half. But notice this covers all the cases. So that's binary search, everybody. So with this, the goal is to try to improve the time complexity for the search problem in this special case when the array is sorted. So, what exactly causes this to have worst case behavior? Notice that in this case, sorry, I was pressing on this chest here. It's pretty fun. If I were to go through this, notice that I'm at the mercy of these recursive calls. Notice that you could actually rewrite this algorithm using just purely iteration. So just using a while loop would suffice. But I'll let you think about that. The point is that every time I make a guess, there's a possibility it's not going to be equal to X. So naturally, if I want to make this happen as much as possible, if I want to make it so that there's this maximum number of recursive calls that happen, the worst case is just going to be simply when X is not in L. Akin to something like linear search, but notice that this will cause us to have to go all the way through all of this work until we reach this point. So there's going to be a case where we're going to have not find X and we're going to have nothing else to evaluate. So we want to make it so it takes in as many possible guesses as possible. So we're going to try to bound this. So the first thing you should notice here is that if we're going to measure the time complexity of this, we need to think about analyzing recursive algorithm. Now, before I do that, I want to give you just a motivation behind the correctness of this algorithm. So I must stress that every time you make a guess here, when you make that guess, it's either going to be equal to that, or if it's not equal, you can guarantee it's going to be sitting in some interval. So its position is going to be somewhere in between that one or this one. Notice the positioning of those guesses. So if you guess at a certain point, so if I make this number of guesses, notice that every time I do it at a given guess at a spot, if it's not equal, then you can tell me it's either in that one or in this one. Like, that's something you could always say about binary search. If it exists, then it will most certainly eventually get this. If not, it most certainly will return -1. You could prove this directly, but you'll find that the cases are going to get a little bit more muddy. But you can use the idea of invariance. I'll encourage you to think about it, to think about how you would come up with an argument using induction like this. Let's talk about the time complexity. So the big thing is that this is a recursive algorithm, and ultimately I want to know 2 questions. if I ignore the recursion, how much work is being done here in one call? So how many operations are happening in just one call? And then the other thing is how many calls are going to happen at most in the worst case? So how many calls are happening in one call, and how many times at most are they going to happen? So if I can answer all 2 pieces of this plus the third, then we're done. So if I ignore the recursion first, this is actually how you could analyze this algorithm. If you ignore the recursion, so you ignore the recursion first, notice that if this takes constant time, that takes constant time. Notice that all of this, I'll let you think about it, takes constant time. So notice that if you take all of this, you could show that this all is, when you ignore the recursion, all of this is just some constant number of operations. So I'll have more details in my notes. But we still have to incorporate the recursion. So for one call of this algorithm, in the worst case, it will be that either it goes to the left half or the right half. So we got right half, left half. Can it do both at the same time? No, right? It only can either do this one or that one. So there's one recursive call at most that can happen, and each one of these calls, there's a constant number of operations. So I'm going to formulate this as a recurrence relation, and we're going to try to find out the asymptotic nature or asymptotic behavior of that complexity function. Once I have that, I have the answer of what the worst case running time of binary search is. So hopefully the game plan is clear. We're going to try to come up with a recurrence relation based on what we just had here. So far we know for each call, one recursive call happens, and each time it's always going to be done on something that's going to be roughly half-ish. We'll see. Plus, every one of the calls does some constant number of operations. So let's put it all together. So here we go. So let's think about how the recursion works here. So I'm going to draw a picture to help us think about this. Okay. So suppose I make a guess. You know it's going to be in the middle here. Now keep in mind there could be more parts to this array. Presume that this is the interval I'm looking at. Suppose I want to know how many operations are happening with respect to this number of elements. So there may be the case that there's no more elements to look at as well. So just keep that in mind. So I'm going to measure it based on how many elements are in my interval when I think about this. So if I currently consider this one, notice that if this is n elements here, how many are over here and how many are over there? Well, let's think about it. If this is n, well, how many elements are left? Well, if that's n and I took away 1 because I already looked at this, we don't want to look at this again. Well, whatever's here, depending on the parity of the length of this interval, it might be even or odd. If it's even, it may be that one side has a little bit more than the other. But if it's odd, they'll have roughly equal size. Either way, it's roughly equal, but in the odd case, you'll notice that it's going to look much more like this picture. But what the point is that this is going to be no more than n minus 1 divided by 2. So notice that if I have this case, notice that if I'm considering the left half or the right half, the number of elements left for me to look at can never exceed n minus 1 over 2. Does everybody see that? So this is going to be an assumption I'm going to make in how I formulate this. So a simplifying assumption I'm going to make so that both halves of the array have the same size. Which is n minus 1 over 2. So what I'm gonna do is I'm gonna call t of n. I'm gonna call my function t. That's gonna be my complexity function. Its input's gonna be n. So I'm gonna let be our complexity function. So we're gonna put everything we talked about together. So some of it I did not write here on the board, so I encourage you to fill in those details, the things we've talked about. So putting it all together, our recurrence relation is as follows. So we're going to formulate a recurrence relation. It's just simply a function that's written in terms of itself. It has what we call a base case. It should remind you of what we talked about recursion over there. It's the same phenomenon, okay? It's just that this is measuring the time complexity of the algorithm. So it's not an algorithm, it's the time complexity of the algorithm based on our analysis. So I have t of n is going to be t of n minus 1 over 2 plus 1 if n is strictly bigger than 0. And we're going to assume that t of 0 is equal to 1. Now, let me just put it all together here for you. There is one recursive call. It's always on one of these two chunks here. This one or that one. So one call happens. This is how many elements you check at most. There's a constant number of operations that happen for each one of the calls. That's it. And t of 0, that's when we have no more elements. That's when your intervals cross over. And there's a constant number of operations that happen there. So this is our recurrence relation that's going to represent the time complexity for binary search. Now, I must stress that if you really are nitpick about me using ones here, you can always relabel these with constants as per how I did previously with something like linear search. So now that I have this, I'm going to apply a technique called iterative substitution or repeated substitution to try to solve the recurrence relation. Now, when I say solve, what I'm saying is I want to express this function without any of the recursive parts in it. So I need to find out a pattern to make this work. So I'm going to say, let us solve, I'm going to put solve in quotation marks, t of n, by repeated substitution to figure out the time complexity. So now you might ask, what is repeated substitution? Well, what it is we're just going to simply try to observe a pattern that we can check, by the way. If we want to use mathematical induction, we can check if this is indeed going to match what we get from this recurrence relation. I'm not going to do that here for the purposes of time. But what we do is we try to expand out the recursive part of this part right here. Remember, it's expressed in terms of itself. So t of n is expressed with itself in it, right? Until it eventually gets small enough. What my point is that we're going to have this where I want to know how many times can I rewrite this equation. But I want to figure out two things. What's happening with the non-recursive work, the stuff that happens other than the recursive call, and what happens, how many times do I have to apply this right here, this recursive call? This is analogous to me performing the recursive case of that recursive algorithm over there. So every time I do this, I want to see how much work gets accrued until I reach the base case, right here for t of 0. So I need to do this. I'm going to keep writing out equations and find out how many equations I need to get to the base case. Once I have this, I'm going to try to tally up almost like I'm collecting it up in a bin, all that non-recursive work, and see how much in total I have at the end of the day. And that'll tell us time complexity. So here we go. So I'm going to expand out this recurrence relation by writing out a new equation for each recursive part. We're going to try to guess a pattern. You would check this with induction if we needed it. But the idea is we're going to try to figure out how many ones I have to write out here. That's all the stuff, all the work I do each time I do a recursive call. So first I have t of n. Well, that's t of n minus 1 over 2 plus 1, right? Okay, what I'm going to do is I'm going to write this right here as a new equation. But wherever I have this as the input, I'm going to write that almost like I wrote n right here. So if this was a banana, I would write banana minus 1 over 2. So this is now the banana. Now I'm going to have to write the banana here where it's banana minus 1 over 2. So watch this. So I'm going to have t of n minus 1 over 2 minus 1 over 2. So I just write whatever the input is where it is. Plus 1. Well, what's this? Well, let me rewrite this a little bit because it looks a little bit funky here. Well, this is just t of n minus 1 minus 2 over 2 squared. So I'm going to end up with an extra 2 that gets dragged down. As a result, I'm going to end up with one of these numbers bumping up to a power of 2. At least it looks like that. Plus 1. I'm going to encourage you to try fiddling around with this. It's t of n minus 2 to the power of 0 minus 2 to the power of 1 over 2 squared plus 1. Now, what you could do is you could take this recursive part, write out a new equation for that. So t of n minus 2 to the power of 0 minus 2 to the power of 1 over 2 squared. Once you see this, you're going to start seeing the pattern we might guess. So when I do this, I'm going to write out whatever this is as the input. Now I would go through the same process that I just did, where I would write this here, but you're going to notice it's going to actually create something very similar to this, but it's going to introduce another power of 2 in similar places. So I end up with n minus 2 to the power of 0 minus 2 to the power of 1 minus 2 squared all over 2 cubed plus 1. So there's something interesting going on here. Does everybody see it? So notice that here, I had 2 to the power of 1. Now it's 2 to the power of 2. And notice the denominator now has an extra power of 2. Do you see that if I were to apply this equation one more time, like if I take this and rewrite out that, you'll notice it should remind you a lot of the previous one, except it's going to have another power of 2. So it's going to be like 2 to the power of 0 minus 2 to the power of 1 minus 2 to the power of 2 minus the next power, so 2 to the power of 3 divided by 2 to the power of 4. Right? So you see how this is starting to form a pattern here. It's not very clear at first. We have to write it in a very specific way to help us see it. But you can keep writing this out, and this is my guess of what this would look like for an arbitrary application of this equation. So here's my guess. But please take note of how many equations I'm writing down. So I started off with just t of n, but when I did one recursive call, it's just n minus 1 over 2. And then it bumps up by 1, then it bumps up to 2, then bumps up to 3. So notice that every single time I apply this, it goes up by each successive power of 2 in the denominator. So it starts at 2 to the power of 1, 2 squared, 2 cubed. So naturally, the next one would be 2 to the power of 4. So here's the idea of what my guess would look like. So I have n minus 2 to the power of 1 minus 2 squared, 2 to the power of 1, all the way up to 2 to the power of j. So you know if it's j here, then it's going to be j plus 1 down here. 2 to the power of j plus 1. This will be equal to t of n minus 2 to the power of 0 minus 2 to the power of 1 minus all the way to 2 to the power of j plus 1. So every time I introduce another power of 2, right? And then the exponent down here always goes up by 1. That's my guess. And you add 1 for the non-recursive work, right? So I have a whole bunch of equations here. So notice that there's two things. First thing is notice that the value of this always decreases. It always gets smaller. It never gets bigger. It gets smaller every time I write out a new equation. The other thing is I want to know what happens when we get to t of 0. So notice the input value given to t on the left-hand side decreases with each new equation. So we stop this process when we reach t of 0, right? We stop this process when n minus 2 to the power of 0 minus 2 to the power of 1 minus all the way up to minus 2 to the power of j plus 1 all over 2 to the power of j plus 2. This is after the invocation of this. So notice I'm looking at the right-hand side right now. I want when this is equal to 0 because then whatever this would be that is a sign t of 0 plus 1. And that would cease the recursive part. So I'm going to put star right here because this is going to be a very helpful equation for us. Then, now I'm going to take into consideration how many equations I wrote down. So what would happen in this case is I would have a whole bunch of 1s that I would add up. And then I would have this invocation at this time. T of n minus 2 to the power of 0 minus 2 to the power of 1 all the way up to 2 to the power of j plus 1 divided by 2 to the power of j plus 2 plus 1. So there's a whole bunch of 1s. So this is what t of n is going to be equal to. It's going to be equal to this. So now, what can we do? Well, I'm going to rewrite. So now we want when this is equal to 0, right? So the input of that recursive call. So this is going to be equal to 1 plus 1 all the way up to when this becomes t of 0 plus 1. But you might ask, Dan, how many equations did you write out? Well, let me rewrite this a little bit more carefully. So I'm going to pull that 1 out of there. And let's think about it. Let's think about it. Okay. How many equations have I written down? Well, I had j plus 1 many. Notice that the number for that exponent in the bottom actually tells you how many equations you actually wrote out. So it's j plus 1 here. So that means that there's j plus 1 many 1s plus 1 extra 1 I just grabbed from right here. So there's j plus 2 many 1s here right here. Well, what does that mean? Well, this is t of n is equal to j plus 2 plus 1. Now, you might be saying, Dan, why don't you just make it j plus 3? You'll see in a moment why I'm not going to do that. You can, but you'll see that this is actually going to be quite nice for us. So now I have actually an equation that connects n up to j, and I would like to know what j is up to. So now we have an equation for t of n. Notice there's nothing involving recursion on that. Now I just need to know what j is. So what is j in relation to all this stuff? Okay, we're almost there. We're almost there. It's a little bit more of a casual day, you see. So anyways, well, we know, so to determine, Sorry, there's a mosquito coming after me. They're coming for the juicy, juicy M word, the mayonnaise and mustard, you know, that math. To determine, mosquito, go over there, to determine the value, out of the way, mosquito, go over there. To determine the value for J, we can use star, right? So notice that in the denominator of star, we had 2 to the power of j plus 2, but we had it so it's equal to 0. So if you multiply both sides by 2 to the power of j plus 2, it just goes away. So now we have n is equal to 2 to the power of 0 plus 2 to the power of 1 plus all the way up to 2 to the power of j plus 1. Which this, if you actually rewrite this is actually a finite series. To the power of I is equal to 0 to j plus 1. So if I'm going to rewrite it like this. And naturally, you might look at this and say, Dan, I might know what that series looks like. That's a geometric series. It's a finite geometric series. This is a finite geometric series. Right? So if you're familiar with the geometric series, it has a radius or like that. Sorry, it's the rate. I'm not going to get too overly technical with the geometric series here. It has a fancy name. So I'm going to call that R. It's R is 2 in this case. So you'd see it's R to the I. Now it actually has a closed form if you recognize this. So this right here, so n is equal to this to the power of j plus 1. Now I'm just going to put in this closed form. It's 2 to the power of 0 minus 2 to the power of j plus 2. It always just goes one higher. Over 1 minus 2, which this is just 2 to the power of j plus 2 minus 1. So I'm going to let you think about how you would formulate this. If you're not sure of the steps here, feel free to ask me about them. I'm very happy to help. Then, now, I'm going to move this minus 1 over to this side. So I have n plus 1 is equal to 2 to the power of j plus 2. And now, when you have something with an exponent like this, and I want to know what j is in relation to n, I'm going to try to get it so j is in somewhere I could rewrite it in a nice way. So watch this. So we're going to move minus 1 to the left-hand side. Then apply logarithms to both sides. And we end up with log base 2 of n plus 1 is equal to log base 2 of 2 to the power of j plus 2. But if you look at this, you see that this is log base 2 of exponent. Well, there's a power rule or power law of logarithms that allows you to pull this exponent out front. Log base 2 of 2 is just 1. Because 2 to the power of what is equal to 2? Just 1. So this ends up just being j plus 2. But here's the thing. We've established that t of n is just j plus 2 plus 1, right? So I'm just going to put in where we had j plus 2, I'm going to put in log base 2 of n plus 1. Therefore, t of n is just log base 2 of n plus 1 plus 1. But if you know your big O, you know that this is big O of log n. which this establishes the time complexity for binary search. So notice that log n is actually much better than linear. So if you know your array is sorted, or you're working with comparable elements and your elements are sorted, if you want even more specific, you can use binary search, which is a considerable improvement on linear search. So that's binary search, everybody. So no questions at all. It's, like I said, it's rather quiet here today. I only have one more thing I'm going to talk about today. I'm not going to spend as much time on it, but I think you'll find it interesting, because I think it's important that I make a remark about this. Okay, let me just erase that board over here, and then we'll get to our last part here. These mosquitoes are just coming at me. They just want a big part of this. Okay, let's get to the last part of this discussion so I could complete everything we've got. Okay, everybody. So up to this point, we've talked about linear search, we talked about lower bound for linear search, and we also talked about binary search, and we established that binary search runs in big O or even big theta log n, which is really nice. Now, a natural question is, if in the case of the search problem, when the array is sorted, is big O of log n the best node running time for the search problem in this special case? And the answer is yes. The answer is yes. I thought I would give you a quick sketch of why this is indeed the case. So the one thing I really need to do to bring this up, so last time I showed you an adversary approach. So to use what we call an adversarial argument, we showed that you require at least big omega n operations to solve the search problem when the array is unsorted. Naturally, you could use that argument and easily extend it if you didn't know anything about the elements, but we know more this time. And in fact, we also know that we can compare the elements. We know that one element could come before another, or if it's equal or not equal, right? That brings me to talking about the idea of a comparison-based model. So we can have different models of computation. So one assumption I made when we talked about, say, linear search, and when I talked about its lower bound for the search problem, the only assumption I really made is that I check if it's equal or not equal, right? It's a pretty broad assumption. Here I'm going to presume that the elements can be listed from smallest to largest. They can be also compared, say one could be less than the other. But I must stress that this is still a rather general assumption, but if you have more specialized knowledge, say for example, you know things about the distribution of where X might be in the array, you could use that information as well. I'm not going to make any presumptions about knowing things like that. I'm just going to know that I just make comparisons. I can tell you if one's smaller than another, if it's equal to X, our value that we're looking for, or not. So we're going to presume that it costs me something to check if an element is greater than, equal, or less than. So this costs, say it costs one operation to do that. Anything else, I'm not going to worry too much about. The other thing is that for the comparison-based model, the model is operating on what we call a decision tree. So what happens is you could ask a series of guesses or questions, and you could ask questions about whether it's greater, equal, or less than. So I say each branch asks a question. And it's one of these three up here. So what would one of these look like? Just to give you an example, is suppose that you have one element, say x1, and you want to say, okay, you have x1 and you're comparing it against an element called y. Now there's three possibilities. So I don't know what's happening with x1 and y. It could be that x1 is less than y. It could be that x1 is greater than y, or x1 is equal to y. If that's the case, then we know that x1 is equal to y. And this is what we would call a leaf node in this decision tree. Every internal node will be a query, a question that's being asked. Every leaf node will be a result, the output of the decision tree. It'll tell you if you found it or not, right? It'll tell you if you found a match. So this could be also recast as a position. So likewise, you could keep asking this kind of question. You can ask the next element. Okay, is x2 in relation to another element? Say it's z. I'm not quite sure what it is. Okay, suppose that instead of it just being this, maybe this is my value I'm looking for. Let's call it, we'll call it v. So every time I keep checking each one of these, and I ask if it's less than, greater than, or equal. When it's an equal, it's a leaf node. You can do the same thing here. Here's x2, and x about v. Now, it might not necessarily be x2. That's the point I'm getting at. It could be a different value that's getting compared here. It could be equal, it could be less, it could be greater. But the point is that whenever we have an equals, we get a leaf node. And the point is that when you formulate a decision tree like this, if you look at the pathways, the path that I take from the top of this tree and I work my way down, every time it dictates a choice. So it tells me something. So this actually corresponds to the idea of asking one of these questions. And when I reach a leaf node, that gives me the decision, the output. So that's how so this is just a high-level view of how this model computation works. So a comparison costs something. Rearranging things doesn't cost anything. Although you wouldn't do that really in this problem. You really care about the positioning of these elements. So a pathway in this is is corresponding to execution of an algorithm, what we would call a comparison-based algorithm, because it's using comparisons. So that's what the path will correspond to in this tree. But remember, the tree itself is a model of computation that we're using to measure how much work is happening here, okay? So there's a correspondence between a path in this tree with, for example, if I were to find that x2 is equal to v, then I would stop right here, right? However, this could keep going downwards. Now, you might ask, how many possible outcomes can there be in this decision tree? Well, let's think about it. If I have an array, and there's n elements in here, right? X could be anywhere in here, right? But each one's a possibility. But there's also the possibility that x is not in the array, the value x that we're looking for. It's not in the array. That's one other possibility. So the total number of possibilities that could happen, which would be leaf nodes in this tree. So the number of leaf nodes is at least n plus 1, right? So that's the number of possibilities that can happen in this decision tree. So naturally a question is, okay, if I know that information, if I could find out what the path, because remember, some of these paths are going to be short, other ones are going to be long. So if I have my tree and I work my way down, notice that the only ones that go to non-leaf nodes, there's two possible pathways. But if you ignore the third one, which exactly will be always going to a leaf node, these will always correspond to a comparison that leads you to another question to ask. So if you look at this, every time you go up by a power of 2, it's going to be something at most a power of 2, right? Every time it's going to be something like a power of 2. But here's the thing. Here's the catch. For our search-based algorithms, when they make comparisons like them, each one will have their own comparison tree like this. It'll have its own decision tree. Sorry, I'm getting very excited here. So each one of these comparison-based algorithms will have its own decision tree like this. And the thing is, I would like to know, okay, so what can I do to tell me how long one of these pathways will be? So if I could find out how many leaf nodes are down here, that could tell me how deep this tree is. Now, as a high-level exercise, what I want to tell you is that if you take this and you combine it with information about how many leaf nodes there are in total at the lowest level, so I want to know how many, this might give you a relationship between the depth or how long this path can be. And how long this path can be corresponds to the worst case running time of a given comparison-based algorithm. And I want to know how long can this be, at least. So how much do you have to do at least? What you could do is you could show that this decision tree, its height, is it going to be, sorry, it's going to be big omega of log n. So the height of this tree, which will be the maximum depth of any one path, which corresponds to the execution of an algorithm for how many comparisons are made. Each comparison will require a cost of 1, which corresponds to doing a constant number of operations in our algorithm. This height is going to be big omega of log n, which is all you need to get the lower bound, because this decision tree over here each will have its own for any comparison-based algorithm that attempts to find this value x in the array. And the point is that there's only n plus 1 many possibilities, and what you'll find is that this number that's on this side will end up being some exponential amount. So you could use the trick that I showed you when we're analyzing binary search to take out the next step. So that being said, that's everything I have to tell you. So notice here that this means that binary search will meet the lower bound of big omega of log n because it runs in big O of log n. And that means that this is among the best known algorithms we have with the search problem when our array is sorted. Sorry, I'm getting very excited here. But yeah, so I thought I would show you some classic lower bound results. I thought I'd give you a high-level version of this so that you get a flavor for how you could come up with another approach. But notice here, the big catch is that we're just not making any assumptions about the algorithm. But yeah, no, are there any last questions? Last questions, don't be shy. Again, it's a fairly quiet day today. But yeah, no, if there aren't any other questions, I'm going to stop right here. I'm going to say thank you so much for coming on out, and have yourself a beautiful day. I'll see you later. Also, of course, tell your friends to come on out. It's a pleasure to have you out. It's always a good time. I'll see you later.